This video will cover the third page of notes on the topic of rational graphs. Let's do a couple of examples. Here we have example number 2, in which we are asked to graph f of x, where f of x is x minus 2 over x squared plus x minus 6. We will be using these steps in order to graph our rational functions. So one of the things that we notice that we need to get our fraction in lowest terms. So let's go back to our example. So the very first thing I'm going to do is I'm going to get my f of x, and I'm going to factor the numerator, and I'm going to factor the denominator. And we can see them in factored form here. We also notice that we also have a common factor in the numerator as well as in the denominator, which means they can cancel out. Remember, we can't go around topless in terms of fractions, so we need to put a 1 in the numerator so that there's something there. We'll talk about what this means in just a second. Going down our list, the very first thing we do is find our domain as well as our vertical asymptotes. So we're going to get our denominator and we're going to set it equal to 0, and that's what we have right here. This should remind us of the quadratic unit where we factored and then set each factor equal to 0 so that we can find these values here. This means that if x is equal to -3 or if x is equal to 2, my function f of x would be undefined. That means that our domain cannot have the point -3, nor can it have x equal to 2. So this is our domain that lists all the values other than those. It will be from -infinity to -3, as well as from 3 to 2, and then from 2 to infinity. This is how we denote that x can be anything and everything except -3 and 2. To find a vertical asymptote, remember one of the things we had to do was to reduce our fraction. So we did. That's what we did right here. And that gave us this f of x. So what we have decided here, these two parts actually create a hole in our graph. We'll get to that in a second. But notice in our reduced form of my f of x, we can see our parent function is 1 over x. We know that it's going to look like this. We know the plus 3 moves it to the left 3. So we already know what the graph kind of looks like. But we also can see that if we let our denominator equal to 0, that will give us our vertical asymptote of x is equal to -3. The next step we're going to do is to go find the horizontal asymptotes. Notice what we're going to do for horizontal asymptotes is we're going to compare the degree of the numerator with the degree of the denominator. And we can see the degree of the denominator is 2, and that makes it bottom heavy because the bottom has a bigger degree than the numerator. And every time it's bottom heavy, we can automatically say that the horizontal asymptote is y is equal to 0. Next, we're going to go find the y-intercept. Remember, to find the y-intercept, we let x equal to 0 and we solve for y. So I am literally coming back to my function f of x. We're going to let x equal to 0. I'll put a 0 up here, a 0 here, and a 0 here. I can also do it down here, put a 0 here and a 0 here, and we find that we get 1 over 3. Notice we would get the same thing here. -2 over -6 is 1 over 3. So that's how we found our y-intercept, 0, 1/3. Finally, let's go find our x-intercept. Remember, that is when we let the numerator equal to 0. If I come up here, we realize that the numerator will never equal to 0. This is in our reduced form of f of x here. So we actually find that there is no x-intercept. And we can try that when we would have 1 over x plus 3. We let that equal to 0. We multiply both sides by x plus 3. We get 1 is equal to 0, which is not true. So we can see that there is no x-intercept. We are now ready to graph. Remember that our f of x in reduced form was the equation f of x is equal to 1 over x plus 3. And we talked about how we knew how to graph that it would be our parent function of 1 over x, and that it would be moved 3 units to the left. That's how we get our vertical asymptote here. We can also graph it by using our information here. We know our horizontal asymptote is going to be y is equal to 0, or the x-axis. And then we also know the y-intercept is 0, 1/3. That's this point right here. So we're ready to finish graphing. We know that from our parent function, we would go over 1, up 1, and then get really close to our asymptotes. Really close to our asymptotes and go all the way in both directions, to the left 1 and down 1, and then towards our asymptotes and towards our asymptotes. But let's talk about this hole that we found. How do we know it's a hole? Remember that we were able to cancel out these factors. When you have this happening, when you have common factors in the numerator as well as in the denominator that they factor out, it creates a hole in our graph. And that hole is when I get that factor, which was x minus 2, and I solve for x, that gives me x is equal to 2, then I need to come over here when x is equal to 2 and erase that point. That's why you see a hole right here on our graph. Let's go to example number 3, where our job is to graph f of x, where f of x is equal to 2x squared over x squared minus 1. We're not going to be doing too much graphing like this, but I do want you to see that we can still apply what we know. So the first thing we're going to do is see if we can reduce that. So we know we can't factor the numerator, but the denominator can be factored into x plus 1 times x minus 1. So we're ready to go find our domain. Our domain is when we let the denominator equal to 0. We have it in factored form. We find that x cannot be negative 1 and x cannot be positive 1. So we've listed our domain here. Because nothing crossed out and we still have these factors in the denominator, we can say that we have two vertical asymptotes, one at x is equal to negative 1 and one when x is equal to a positive 1. To find the y-intercept, we go back and let x equal to 0, and we can put 0 everywhere we see our x's, and we can see that at the top we're going to have 0 and at the bottom we're going to have negative 1. That is still defined. It's just that it's equal to 0. So that means we have our y-intercept of 0, 0. When x was 0, the y value was also equal to 0. To find the x-intercept, we let the numerator equal to 0. So that's how we get 2x squared minus, that's how we get 2x squared is equal to 0. Divide both sides by 2. Then I get x squared is equal to 0, square root both sides, I find x is equal to 0, and again I find the x-intercept to be 0, 0, which is the same as the y-intercept. That just means we get 1 point on our graph. The only other thing that I want to make sure you're able to do is to be able to find vertical asymptotes, which we just talked about, as well as being able to find horizontal asymptotes. For horizontal asymptotes, we're going to compare the degrees of the numerator with that of the denominator. So when we come back up here to our f of x, we see that the numerator has a degree of 2 and the denominator has a degree of 2. So we say that they're equal heavy. Degree of the numerator is the same as the degree of the denominator. We get the leading term of the numerator and the leading term of the denominator, and we make a fraction so we can compare those two. We can see that the x squares will cancel out, and then we just have 2 over 1, which will give me just 2. So we found our horizontal asymptote is y is equal to 2. I may not ask you to graph as you see here, but you should still be able to find vertical asymptotes, which we were able to do that by just using the equation. We should be able to find horizontal asymptotes. Again, we just used the equation. You should also be able to find y-intercepts and x-intercepts, and again, we use that by just using the equation. So you may not have to graph, but you should be able to tell by looking at the equation how many or what are the vertical asymptotes, and as well as what is the horizontal asymptote. And that concludes this video.